This is the second part of the 21st lesson in heat transfer. In the second part of the 21st lesson, we will be looking at the equation for how the mean temperature of the fluid changes in the flow direction. In the first part of the lesson, we thought through this variation in a qualitative fashion without doing any mathematics. We only applied what we understood to be true about the physics of the heat transfer. In this lesson, we will use an energy balance on an appropriately defined control volume in order to derive an equation which will allow us to calculate the mean temperature at any location in the tube. By the end of this lesson, you should be able to use an energy balance on a section of the flow in the tube to relate mean temperature changes to the applied uniform flux. You should also be able to identify the governing equation for the mean temperature of a fluid flowing in a tube with a uniform wall flux. On with the lesson.
First, making it possible for us to calculate the mass average temperature of the fluid anywhere in the concentrator. So if someone said, what's the average temperature of the fluid halfway down the concentrator? You could make the calculation. We actually don't need heat transfer at all for this particular question because we know what the rate of heat transfer is across the wall. So to answer this question, we're going to draw a piece of the tube from the inlet to some location X down the tube. So we've got fluid, the oil flowing through here, this tube. It's flowing at a known mass flow rate. The fluid enters at some known mass average temperature at the inlet. And it comes out at some temperature over here. And we're going to say that that's X position down the tube. So this is some position X down from the entrance of the tube. Okay? And the fluid has some specific heat, right? So the fluid has some specific heat in here that's given to us. So a known CP. And CP is equal to a constant. So inside this fluid has some specific heat, it's equal to a constant. And at the boundaries, right, we have the constant flux applied over the surface. We have a constant flux, and the tube has also some diameter d. So this is you're going to all do this work, but basically what I'm saying is we're going to define a system to be this section of the tube, and we're going to apply our energy balance equation, accounting for what we know to be how we can relate the energy associated with the fluid flowing in, right? Because we have this mass average temperature. So I want you to apply the energy balance equation. And get an equation for the mass average temperature of the fluid coming out at any X location. So get Tmx equal, right, some function of X, right? So I want you to figure out what this function is. What is the function of X that allows you to calculate the mass average temperature of the fluid? So give yourself 2 minutes to try on your own.
Now, what I would like you to do is pause the video and write down an answer to the question.
So I think we've all pretty much got it at this point, but you can check. So we're applying the heat transfer energy balance equation. So E dot stored is E dot in minus E dot out plus E dot gen. It's a steady flow problem. Like we're saying that the fluid's been flowing through there for a long time, so it's steady flow. There is no thermal energy generation. So we have as 0 is equal to what's going in minus what's going out. What's going in is some enthalpy that's being carried by the fluid. And I can formulate that enthalpy using the mass average temperature. That's the value of the mass average temperature. I just multiply by m dot c sub p, and I get the right energy flow rate. I also have energy coming in with the applied flux. I got to multiply by the right area. The right area is going to be the surface area of the section of the tube, which is its circumference times its length, x. And then energy flows back out with the fluid at the place where we cut the tube and sectioned it and looked at it. So this is the surface area of the tube, which for us was pi dx, of course. But I also want you to encourage, I want to tell you, you should think of that as the perimeter times the length, right? So this is the perimeter. Because then, even if it wasn't a tube, if you have some other shape, it's exactly the same formulation, right? So if you had a square, you'd still have the perimeter times the length because that would be the surface area of like a square duct. Or if it was a triangular duct or a star-shaped duct or whatever, right? If you take the perimeter and multiply by the length, you get the right surface area. So I'm going to make that substitution, and then I'm going to solve for TMX. So I'm going to divide the whole thing by m dot c sub p. So I have T m I plus the flux times P times X over m dot Cp minus TMX. So that means solving for TMX, right? TMX is TMI plus the flux times the perimeter over m dot times the specific heat times X. That is an equation for the mass average temperature of the fluid at any position X. You tell me what X is, I'll tell you what the temperature of the fluid is there. Of course, I have to know what the applied flux is. I have to know something about the geometry of the tube, the flow rate and all that, but that's all given. This is equation 840 in your textbook. Okay. We got there together. I think it was valuable to go through this exercise. So we've got that now. We can calculate the mass average temperature anywhere. And if we take the conditions given on page 1 of your handout, we can actually do the calculation for one of these parabolic trough concentrators. And I'll just show you, I'm just using the values given to you here to give you a sense of how much temperature rise you get across one of these 17 meter long parabolic trough concentrators. You plug in, this is the flux, it was 20 kilowatt per square meter. This is pi times the diameter, right, over m dot is given to us, 2.5 kilograms per second, times the specific heat was 2590 joule per kilogram Kelvin. And then I just put in X equal L because I wanted to know it at the outlet. Right? And it's 17 meters long. So you get a 12 degree C rise in temperature over this thing. Doesn't seem like much, right? But 2.5 kilograms per second is like really hauling, right? So if you imagine a kilogram of, just imagine a kilogram of water. You have a picture of how much that is? Like that's, you have a sense of what a kilogram is, yeah? So imagine that flowing through the tube, a 17 meter long tube every second. That's really moving fast. Yeah? So there's a high flow rate. And so there's not a whole big temperature rise in one concentrator, but you have to remember that the field is made up of hundreds of these things and they connect them in series. So you take the one, it starts at 400, it goes to 412, and then that becomes the inlet to the next concentrator. And you get another 12 degree rise, another 12 degree rise, right? Depending on how you laid your field out. And then it becomes a game of how many do I put in series versus how many do I put in parallel, right? To ultimately get some target temperature that I want for my power block, which is going to run the Rankine cycle and produce electricity. So that's the kind of the game that they play in designing those fields. But this is the essence of, like, this is how they, roughly speaking, this is how they calculate the temperature rise across any particular concentrator. Right? They have some idea of what the applied flux is going to be and how much energy is going to go in. And they calculate the average temperature rise this way.